All right, so we have a few example problems we're going to run through here. So the first one is different solutions, same concentration. Okay, so suppose you create 0.1 molarity solutions of copper 2 sulfate, sodium hydroxide, and potassium chloride. For equal volumes, which solution will have the most mass? So the mass of each solution is going to be the mass of the water plus the mass of the solute, right? So mass of solution equals mass of water plus mass of solute, right? We're just taking everything and we're just adding it all together. So the mass of the solute depends on the molar mass. Right, so we need to find the molar mass of these substances. And then to determine the mass corresponding to 0.1 moles of each solute, we're going to have to multiply the number of moles by the molar mass of each compound. All right, so let's start with copper 2 sulfate. So the mass of copper 2 sulfate. So first we take the molar mass, which in this case, if we added it all up in the periodic table, right, we just add copper plus sulfate and 4 oxygens. That would be 249.7 grams per mole. Okay, and we take that number and we times it by, in this case, our molarity, which is 0.10. That's moles over volume. Moles over liter. And if we do that, moles cancel out. And then we get 25 grams of copper sulfate. Okay, so we're going to hold on to that number here for a second. Okay, so the next one is sodium hydroxide. Same thing, find the molar mass for sodium hydroxide, which in this case is 40.0 grams per mole. We take that same number we started with, 0.10 moles per liter. Moles cancel out again. And this time we get 4.0 grams of sodium hydroxide. Last one, mass of potassium chloride. So that is the molar mass for potassium chloride added up. It's 74.6 grams per mole times 0.1, and that will get you 7.5 grams of potassium chloride. So to answer the question, which solution will have the most mass, it has to be copper sulfate. Right? It has quite a bit more mass than the other two. So this is a way to compare substances. You'll have to be able to do this in the problem set for this lesson. So make sure you are familiar with that. Again, it's basically just the molar mass times the molarity, which will be given to you. All right, so for number 2, looking at each solution, determine the molarity and the density of each solution. So if you remember the density, that's just grams over liters, right? So we'll just start by taking the density and solving for that first. Just because we don't have to do any extra steps, we're just going to do, for the first one, 1.5 grams divided by 2.0 liters. And if we do that, we should get 0.75 grams per liter. Okay, so that's our density for this one. And then if we need to find the molar, or not the molar mass, the molarity, we have to use the molar mass, right? So 0.75 grams per liter, we can go ahead and take the molar mass, which we just did above. It's 74.6, and we're gonna put that at the bottom. All right, so 74.6 grams per 1 mole. Right? So we just took the molar mass and we flipped it upside down. That's so the units cancel. And then what we should get, take 0.75 and we divide it by 74.6, and you get 0.010 molarity. All right, so that's our density, and this is our molarity, or concentration of potassium chloride. All right, so the next one, 8.5 grams of sodium hydroxide divided by our volume, which in this case is 0.4 liters of water. And if we do that, we should get 21.25 grams per liter. All right, so that's our density. And then we need to find the molar mass, which I'm just going to steal from the problem above, right there. So 40 grams per mole. Again, I'm going to put that at the bottom per 1 mole. Our grams cancel out. And then we take 21.25 and divide it by 40. That's going to equal 0.531 molarity. All right, this is something you also have to do on the problem set. You'll have to be able to convert using density and the molar mass to find the molarity or concentration of different substances. All right, so last page. Talking about toxicity and talking about concentration, it's kind of important, it's really important how regulations or things like the EPA, the Environmental Protection Agency, limits the contaminants in drinking water. So they are constantly testing concentrations and different, all types of water from different companies to cities, and basically making sure that the water is safe to drink. So looking at this, we're looking at the maximum contaminant levels for fluorine, iron, and barium in drinking water. And they're given some data here for the 3 problems. And so we basically want to find out which one is the most toxic. Okay, so what we have to do is find the concentration of the potential toxins in moles per liter. So what we're going to do, we're going to convert the maximum contaminant level milligrams to grams, and then we're going to divide by the molar mass. Okay, so we'll just do this one by one. So this is kind of step 1, and then this is step 2. To start, we'll do fluorine first. So if we take that milligrams, and we need to convert it back into grams, so we basically take that decimal place and move it over 3 times. So we're left with 0.0040 grams per liter. And then we take that and we times it by the molar mass. Molar mass of fluorine is 19 grams per mole. Those cancel out. And so 0.004 divided by 19 is 0.0021 moles per liter. Okay, and we can actually rewrite this, right, as a scientific notation where we use exponents. So 2.1 times 10 to the 1, 2, 3, 4, negative 4. And that's our molarity for fluorine. Moving on to iron. Again, we're going to convert this number here into grams per liter. So that's going to be moving over 3 times. So 0.00030 grams over liters times our molar mass, or in this case divided by our molar mass, which is 55.8 grams per mole. And for that, we get, I'll just write it in, well, I'll write them both. 0.000054 moles per liter, which also equals, or is the same number as in scientific notation, 5.4 times 10 to the negative 5 molarity. last one, barium. Again, just going to convert 2.0 into grams per liter. So that's going to be 0.020, lots of zeros, grams over liters, times the molar mass. And the molar mass for barium is 137.3 grams. Just cancel out. And we're left with 0.000014, which we're going to rewrite as 1.4 times 10 to the negative 5 molarity. All right, so we have these three numbers now, and we want to be able to apply these to different types of questions. So to scroll down here, which is the most toxic? So for this, we actually want to think about which number is the smallest. And if we look at these three, I know it's kind of hard to see with these scientific notations, but barium is actually going to be the smallest number. All right, and we can kind of see that if once they're all written out. Okay, so barium's our smallest. And the reason why is, well, the reason why it's the most toxic is because this is basically saying the EPA is regulating or restricting this amount of barium per liter of water. So the lowest amount really means it's the most lethal. Okay, so it's the most toxic because it is the most restricted of the three. If we look at fluorine, fluorine's number is a little bit higher. That means you can have more fluorine per liter of water, and it'll still be safe to drink. All right, so that's just a little example of how you can use molarity to find the purity of substances as well as the purity of toxins. And that is it for this video. So if you have any questions, let me know. I'm Mr. Mulholland, and this was a chemistry video.